In this videocast, we'll look at the titration of a strong acid with a weak base. We'll take a look at a titration curve and how they look depending on what types of acids and bases, strengths we use. And then we'll take a quick look at polyprotic acids and how their titration curves differ from other monoprotic acid titration curves. Step number one, let's take a look at this sample problem. Calculate the pH in the solution formed by adding 10 milliliters of 0.1 molar HCl to 20 milliliters of 0.1 molar NH3. Remember, the steps when you encounter an acid plus a base is to first write the balanced chemical equation. Step number one, balanced equation. Step number two then is to write an ice table and find out which thing is going to be completely used up and therefore what's left over. And then number three, ask the question, what drives the pH? What drives the pH? What thing or things are created or left over that cause a pH to be higher or lower or changed at all? So step number one, let's take HCl and let's react it with some NH3. HCl plus NH3 now, we'll get some NH4 plus, and we'll get some Cl minus. So write a nice table for this. And then don't forget, when you're going to do the balanced chemical equations ice table, you must be in moles. It has to be in moles. I forgot to write that down here, but don't forget, it's got to be in moles. So lots of times you end up using the molarity triangle. Remember, molarity is equal to moles divided by liters. And we want to find moles, so that's equal to our molarity times our liters. And for HCl, we're told we have 10 milliliters of 0.1 molar HCl. So 10 milliliters, I'm sorry, 0.1 is the molarity right here, times our number of liters, 1, 2, 3, times 0.01. So we have 0.001 moles of HCl to start with. In NH3, we're told we have 20 milliliters of the 0.01, so that's going to start out as 0.002 moles. None of this and none of this to start with. And now you have to decide what's going to get used up. Well, of course, the thing that's smaller is going to get used up, so I'll lose 0.001. I'll end up with none here, lose 0.001, and I end up with 0.001 amount of NH3 remaining. And over here, I gain 0.001, and I gain 0.001 of the Cl minus. So I end up with 0.001 here and 0.001 here. Now, if you're an astute studier of acids and bases, you know that Cl minus is the conjugate base of a very strong acid, and so it's going to do nothing in solution, and therefore it's not going to drive the pH. And this, we're on to step three now. What drives the pH and decides whether something is going to be acidic, basic, or neutral? HCl will do nothing, of course, because we have none left. There's some weak base left. There's also some of its conjugate acid remaining. And then lastly, there's some of this Cl minus, but we already talked about how that's going to do nothing in solution. If you're a good recognizer, you can now see that we've got a weak base and its conjugate acid. These solutions are called buffers. In buffer solutions, you can calculate the pH from simply by taking pH, the Henry Hasselhoff equation, which is pH is equal to pKa plus the log of the base concentration over the acid. So what we need to know is the pKa of the acid right here, which is NH3. And I believe we can find, we will not find the Ka of NH3 in the back of the book, but we will find the Kb of NH3 in the back of the book. And I think the Kb for NH3 is 1.8 times 10 to the negative fifth. And if we take the negative logarithm of that, we get about 4 pKb. Now this would be about 4.7, I'm going to approximate it, 4.76 or so. Now if we want to find the pKa, of course we subtract that from 14, and 14 minus 4.76 is exactly 9.24. So putting it into the Henry-Hasselhoff equation now, we have pH is equal to 9.24 plus the log of the base concentration divided by the acid concentration. Now remember, we did add some solutions here. We have 20 milliliters of this and 10 milliliters of this, so we have a total of 30 milliliters. And remember, we did our calculations in moles, but watch what happens here. This happened in some sample problems in the last video cast. The concentration of the base is 0.001 moles divided by our total number of liters, which is 0.03 liters. The concentration of our acid is also 0.001 moles divided by 0.03 liters. Notice the 0.03 liters cancel out, and look at this. The number of moles is also equal to each other, and so this cancels out as well. And so as an effect, what we're doing is we're taking the log of 1. If you're not sure what the log of 1 is, type it into your calculator, but I can assure you that the log of 1 is equal to 0. And so what happens is our pH is equal to our pKa. And this is a really interesting point for us to study in terms of titrations, because where are we? We're at the point right now where we used up half of the initial amount of moles of NH3. And remember, the equivalence point is when we have equal amounts of moles of base and acid. Here we're halfway to the equivalence point. At the halfway to the equivalence point of any acid weak base titration or any weak base acid titration, you're always going to be at a point where the pH is equal to the pKa of the acid or the pKb of the base. And our pH, of course, is equal to 9.24, which is the pKa of the acid NH4+. Let's take a look at what a graph of something like this would look like. If you want to open your textbook and get a little bit better picture of it, you're more than welcome to. But I'm going to look on page 739 and just zoom out so we can get a little bit better picture of this. Or maybe zoom in, I'm sorry. You can see here we'd start at a decently high pH because we have a weak base called ammonia, and we're going to add some acid to it. And then as we add some acid to it, the pH decreases. This is pH on the vertical axis, and then this is my milliliters of my hydrochloric acid that I'm adding. When I get halfway to the equivalence point, I'd be right here in this region. And notice that this region, the pH doesn't change very much at all. And you can see that the pH is about 9.24. Oh, hey, that was the answer to our last problem. Remember, 9.24 is what we found out the pH to be. And halfway to the equivalence point, notice the pH isn't changing very much. The slope is very, very flat. And this is because during this portion of the titration, we have what's called a buffer solution. Because notice, we have some NH3 present, and we have some NH4 positive present. A base, a weak base, and its conjugate acid are both present in significant quantities. And remember, a buffer is something that resists change in pH. So during this titration, we've created a buffer solution during this point. Now once we break the buffer and add too much HCl, now the pH jumps quickly and dives down here until we hit the equivalence point where we have equal amounts of acid and base. Notice at the equivalence point, the pH is a little bit below 7. The equivalence point does not mean that we're going to have a pH of 7, especially when you have weak acids and bases involved. If you have strongs involved, then yes, the pH will equal 7. But in this case, remember, we had a strong acid being added to a weak base. And when you add that, then you're going to have a more acidic equivalence point. You can probably guess where the equivalence point would be if we had a strong acid with a a strong base with a weak acid. Then you could actually say that the equivalence point would be above 7, somewhere up here. Anyway, At the halfway point to the equivalence point for a weak base or for a weak acid, you can find that the pH is equal to the pKa, or the pKb of a base, if you're looking at it that way as well. Lastly, let's take a look at this graph. This is a graph of what's called a polyprotic acid. And the polyprotic acid example they give here, polyprotic example acid that they give here is phosphorus acid. And when weak acids that contain more than one ionizable hydrogen atom react with OH-, it occurs in a series of steps. Neutralization of H3PO3, which is phosphorus acid right here, proceeds in two stages. First of all, the H3PO3 reacts with some OH- until it starts to produce a lot of H2PO3 right here, and it jumps quickly. It jumps quickly and forms an equivalence point right here. Then it becomes a mix of H2PO3 and some HPO3 2- right in here, and is another buffered solution right here. And then of course it jumps quickly again right here, until we form all HPO3 2-. The neutralization steps of a polyprotic acid, or it could be a polybasic solution, are sufficiently separated, and therefore the titration curve with multiple equivalence points could be used to determine the Ka1 or the Ka2 of a polyprotic acid. And you can use this to determine what type of acid or what type of base you have, as we'll see in a sample in a lab that we're going to do coming to a lab near you soon. So to summarize just a little bit about titrations, let's go through the steps and a couple of the important points of them. First of all, titrations, remember, when we take an acid and add it to a base, and we make some type of salt. I'll just give it a positive ion and a negative ion, and then we also get some water, and of course the water is not going to affect the pH. If the acid and base are both strong acids and base, it will form ions over here that have no effect on the pH. So if it's a strong plus a strong, the equivalence point will equal a pH equal to 7, and we'll have a neutral solution when we're at equal amounts of acid and base. Remember, when we have equal moles of acid and base, we're at what's called the equivalence point. Now, if we have a weak acid and we have a strong base, a weak acid and a strong base, now when you reach the equivalence point, all of the base will be gone, all of the weak acid will be gone. But remember, once the weak acid is used up, it's going to break up and it's going to form a negative ion over here that will be its conjugate base, which forces the solution to be slightly basic at the equivalence point. Slightly basic at the equivalence point. A lot of people think that, oh, because you have a strong base, it's going to be a little bit basic at the equivalence point. That's not really the reason. The reason it's slightly basic is because the weak acid has formed its conjugate base, which gives you a little more OH-. Now, if you have a strong acid and you have a weak base, strong acid and a weak base, now what's going to happen at the equivalence point when you have equal moles of acid and base is all the acid will be used up, all the weak base will be used up, but you will form some positive ion over here that will be the conjugate acid of this weak base, and therefore it will be slightly acidic at the equivalence point. Slightly acidic at the equivalence point. And a lot of people think, oh, since I added this strong acid, of course it's going to be acidic. No, the strong acid is completely used up. The reason it's acidic at the equivalence point is because you have some conjugate acid from the weak base present there. Now, if you have a weak acid and a weak base, then you're not quite sure where your equivalence point is going to be. It depends on the strength of this weak acid and this weak base, and you have to run the equilibrium calculations to figure that out. Lastly, if you draw a pH titration curve where pH is on the vertical axis and volume of titrant is on the horizontal axis, and let's say that we start with an amount of 1, 2, 3, we'll put 7 right here and 14 way up here. So if you start with an amount of a strong acid down here, remember that it will increase gradually as titrant is added, and then there'll be a steep jump in the titration curve, and then it will level off up here at the top once again. And if it's a strong acid and a strong base, remember you're going to get a pH at the end of about 14 and a pH at the beginning of about 1. This is with a strong acid and a strong base. So strong acid starts here, strong base ends here. If it's a weak acid, remember you're going to start at a higher pH, maybe 3 or 4, something like that. And it will still go up just like it does normally. But then remember your equivalence point is going to happen a little bit higher if you're ending up at a strong base. And so here, I'm not sure if I wrote it exactly real good, but the equivalence point was at about 7. And here the middle of the steepest part of the curve was a little bit above 7, somewhere around 8 or 9. And this is because of the conjugate base that's formed when the weak acid is completely used up. If we start with a strong acid and we have a weak base, remember it will go up ever so slowly, maybe slower than it was before, and then it will go up and level off a lot lower than it would with a strong base. So this is a weak base right here, and we started with a strong acid, and you'll notice that the steepest part of the curve has a middle somewhere below 7, and the reason it's below 7 is because the weak base has formed a conjugate acid at the equivalence point where there's equal number of moles of acid and base. One last word. A lot of people hear this all the time. They hear the word equivalence point. Equivalence point, a lot of people get confused about that, and they think equivalence point is when there's a pH of 7. The only time the pH is 7 at the equivalence point, remember, is when there's equal amounts of strong acid and strong base. Equivalence point simply means that the moles of acid are equal to the moles of base. And if it's a weak acid or a weak base, remember that is going to form a conjugate which drives the pH at the equivalence point. Good luck with your titrations.